This is our last learning video on the topic of temperature. I want to make sure you're clear on how to calculate some basic temperature measurements. Meteorologists often report the maximum and minimum temperatures of a given day in a place. Other measurements that are based on those maximum and minimum values include a daily mean or average temperature, a daily range, and a monthly mean. So let's make sure you know how to do that. The daily mean is simply going to be calculated by taking the maximum temperature recorded plus the minimum temperature recorded, and then dividing by 2. It gives us an average. The daily range is going to be calculated by taking the maximum temperature and subtracting the minimum temperature, and that gives us the range of temperatures for a given day. Monthly means are going to take the daily means throughout the month, add them up, and divide by the number of days in the month. If you have a month that has 31 days in it, you're going to add the 31 temperature means and then divide by 31. Other measurements include annual means and annual ranges. The annual temperature mean is calculated by adding the 12 monthly means and dividing by 12. The annual temperature range is figured out by taking the maximum monthly mean and subtracting the minimum monthly mean. So max monthly mean minus min monthly mean. It's a good tongue twister. Here's an example for you to try. Put the video on pause and see if you can use these numbers to calculate the daily mean and the daily range. So the daily mean is calculated by adding the maximum and the minimum and divided by 2. You get 74 degrees Fahrenheit. The range is calculated by taking the maximum and subtracting the minimum, so the range on this particular day was 24 degrees Fahrenheit. We're going to be looking at a lot of diagrams like this that show annual temperature means. And also, a lot of what I'm going over in this particular video is going to come up when you're doing Lab 6. Along the bottom, we have a full year represented in time, January, February, March, etc., all the way to December. Then on the y-axis, we have temperature, either in Fahrenheit or centigrade. And so in yellow, for example, we have the average daily highs calculated throughout the year. And again, these are monthly means that have been calculated for each month. In green, we have the average daily lows for this particular location. And then we can look at the graph and figure out the range just by looking at the difference between those. So, for example, in December, the difference is about 10 degrees Fahrenheit, and so that was the temperature range. This graph also shows record daily highs and record daily lows. Notice that you can tell that this city is in the northern hemisphere by this graph. And that's because the highest temperatures throughout the year are in May, June, July, August. In southern hemisphere cities, we're going to see inverted curves where the highest temperatures are going to be in the January and December regions. So what controls temperature in an area? Well, of course, we've talked about seasons and the incoming solar radiation, and that's very important. But other controls include the differential heating of land and water. And this is actually a huge factor in some locations. Land heats up more rapidly than water. It also cools down more rapidly than water. And in fact, water is the least resistant to temperature change of any substance. For example, if you take a pot of water and you put it on the stove to boil it, and you start with a pot and water that's all at room temperature, what gets hot first? The pot, because the metal readily changes temperature and the water takes more time. Similarly, if your mom bakes you a nice apple pie at Thanksgiving and it comes out of the oven and she tells you to wait until dessert, but you can't because it smells so good, you cut a piece. What part is easiest to eat first? The crust. The filling is much hotter because the filling has a lot of water in it, and it's going to take more time for that to cool down. So here's an annual temperature chart that shows this influence of water versus land. Sometimes we call it a maritime influence. So here we have two cities that are at roughly the same latitude, and that's important because we don't want too many variables. So in theory, they should have the same temperature range. Well, Vancouver is near the Pacific Ocean, and the Pacific Ocean, again, does not change temperature very easily. Winnipeg, on the other hand, is in the middle of the North American continent, and it's surrounded by land, and land heats up and cools down quickly. So throughout a year, Vancouver's temperature is relatively small in its range, Whereas in Winnipeg, it gets very cold in the winters, and it even gets a bit warmer than Vancouver in the summer. So this huge temperature range is the result of it being in the middle of a continent. Hawaii is a good example of a place in the middle of the ocean where the temperature is very similar all year round, and that's again because of the fact that it's surrounded by ocean water. Other things that influence temperature include altitude, and this one is pretty logical. If you go up to Mount Wilson from Pasadena, it's colder. Here we have two cities, La Paz and Concepcion, that are at about the same latitude, but La Paz is up in the mountains. It has a high altitude, and Concepcion is down in the plains. So throughout the year, Concepcion's temperatures are quite a bit higher than those in La Paz. Notice that these are southern hemisphere cities, which you can tell because the coldest temperatures are in June and July. Wind direction is another influence on temperature that's related to land and water's cooling properties. Here we have Eureka and New York City, again at approximately the same latitude. Weather moves from west to east around the Earth, and so do the winds. So Eureka gets its wind that comes over the Pacific Ocean. And remember, the temperature over the Pacific Ocean is going to be fairly consistent throughout the year. New York City is going to receive its wind after it's traveled all the way across the continent. So in the summertime, when the continent gets very hot, the air that arrives at New York City is very warm. In the winter, when it's very cold on this continent, New York City receives very cold winds. And so you can see the difference between these two cities that are in different positions related to the wind direction. Sometimes we call it windward when the wind is hitting something directly, and leeward after the wind has passed over other features and arrived somewhere. So important controls on temperature include altitude, right? The higher the altitude, the colder it's going to be. The geographic position, how far are you from the equator? Cloud cover, which I haven't mentioned yet, and I will in the next slide. And albedo. Remember, albedo is the reflectivity of something on Earth's surface. So if you have a dark forest on Earth's surface, dark colors absorb heat, and that's going to be warm. It's going to make a local area of warmer than normal temperature. On the other hand, if you have a fresh, snowy ice field, that's a white color, and that reflects light, and that's going to be a little pocket of colder temperatures. So let's look at clouds. You're probably pretty aware that when it's a cloudy day, it's cooler outside than when it's a sunny day. And that's because the clouds are blocking the incoming solar radiation. It's not reaching the ground. But at night, there's also an influence. At night, when the Earth is re-radiating its heat, it gets trapped if there are clouds, and it makes the nighttime warmer. So if you've ever experienced a cloudy evening, you'll notice it's warmer than when it's completely clear. So the overall result is that the daily temperature range is lowered when there are clouds. So look at this diagram. This is not showing a year now. This is just showing 24 hours. So we've got midnight, 6 a.m., noon, 6 p.m., midnight. And on a clear day, as shown in red, we'll have the coldest temperatures before the sun comes up. And then it'll warm up throughout the day to some maximum value, and then it will go back down. If it's overcast and cloudy, then it won't get nearly as cold at night, but it also won't get nearly as warm in the daytime. So the overall range is diminished when there are clouds. We're going to finish up by looking at world distributions of temperature. And on temperature maps, lines of equal temperature are called isotherms. They're adjusted to sea level because places that are high in the mountains would be abnormally cold. And we use January and July for the temperature extremes. Now, why would we do that? If the solstices are in December and June, why would we use January and July? Well, it turns out there's a delay between the time when the maximum temperature is reaching the Earth and when the Earth actually experiences the highest temperature. So January is usually colder than December in the Northern Hemisphere, and July is usually warmer in the Northern Hemisphere than June. This is similar to what happens throughout a day, if I jump back to this picture. At noon, when we have the most sunlight hitting the Earth, we don't usually have our maximum temperature. It's hottest usually around 2 or 3 in the afternoon. And so again, there's a delay between the time that the maximum sunlight is hitting the Earth and when it actually produces the warmest temperatures. So here's a picture to show you isotherms. This one right here, I've highlighted in pink. This is the isotherm between the 10 and 20 degree temperature ranges. Then we have an isotherm here between 20 and 30. This one's between 30 and 40, etc. So we're going to be looking at weather maps quite a bit over the next few weeks, so make sure you're clear on what an isotherm is. Here's the world mean temperature adjusted for sea level in July. And again, we use July because that's when the temperature in the northern hemisphere is warmest, even though June is the solstice. And you can tell this is July because if you look, here's the equator, and the warmest temperatures are north of the equator. And notice that they are concentrated on the land. In January, the southern hemisphere is experiencing its summer, and the hottest temperatures are again on land in the southern hemisphere. Notice that we have a very cold pocket up here as well in the northern hemisphere. So the temperature decreases as we go from the equator towards the poles, and that makes sense. Isotherms actually shift with the seasons. If I showed you month by month, you would see that those isotherms kind of march to the northern hemisphere and then back down to the southern hemisphere, and they shift with the seasons. And the warmest temperatures and coldest temperatures occur over land, for the reason I mentioned earlier that land readily heats up and cools down compared to water. In the southern hemisphere, you might have noticed that the isotherms are straighter. They're more stable. And let me jump back to show you that. So here you can see the isotherms in the southern hemisphere are very straight, and in the northern hemisphere they're kind of wobbly. Same with in January, they're kind of straight, and in the north they're kind of wobbly. And that is because the southern hemisphere has more water, and so there's less variation in temperature. So the temperature range is smallest near the equator. The farther you go from the equator, the greater the range is over the seasons. And again, it's greatest over the continental locations. Coming up next, we're going to move on to Unit 5B, Water in the Atmosphere.